Okay, so we will use our reaction between hydrogen and oxygen from our previous slide as our example for this problem, right? Where it's asking us um, how to, or how, you know, it's asking us um, if we had 150 grams of hydrogen gas and 1500 grams of oxygen gas, right? How many grams of water can form, right? So this is actually a very practical limiting reagent kind of question because hydrogen gas and oxygen gas combine together to make water in a hydrogen fuel cell, right? So it's a very practical application. And so for this particular question, it looks like I'm asking you limiting reagent, but like, dang, there's only 150 grams of hydrogen. And there's 1,500 grams of oxygen. Obviously, the limiting reagent is going to be the hydrogen, right? Well, it's not always that obvious, and so you actually have to go through and do your stoichiometric calculation with both of the reactants and figure out which one is the limiting reagent by the one that creates the least amount of product, right? So we'll go ahead and do that now. And this is how you do all limiting reagent problems, okay? So we'll start out by saying, we'll start with hydrogen because it's first in the reaction right there, right? So I have 150 grams of hydrogen gas, right? Because it says right there 150 grams of hydrogen gas, okay? I got to convert that to moles, so I know that there are 2 grams of hydrogen gas, right, for every 1 mole of hydrogen gas, right? Because hydrogen is 1, right, and times 2, because there's 2 of them there, is 2. And again, I always forget to do my states, so don't forget to put your states in there too. It just kind of helps you remember things. So now that I've converted the hydrogen gas from grams to moles, I need to use the molar ratio. And this is why the balanced chemical reaction is so important. For every 2 hydrogens, I have 2 waters. So for every 2 moles of hydrogen gas, that looks really messy. I'm going to fix that. I'm also going to fix this too because it looks messy. It bothers me. I'm OCD that way. H2 gas. There we go. H2 gas. We have 2 moles of water, which is a liquid. So, yep, don't forget, this is the molar ratio. And you can only get that from getting the balanced chemical equation, and it's super important. It will all be wrong if you don't do that. So now that I have moles of water, I've got to convert that to grams of water. So I know that 18 grams of water is equal to 1 mole of water. That's because oxygen is 16, and then 2 hydrogens added together makes 18. Liquids, both of them. And now just go through and do the math here. Multiply 150 times 2 times 18, and then divide all by 4 because 2 times 2 is 4. And so the number I get here is 1,350. It even gave, so this is nice, right? They gave you here 2 significant figures, so you need to do it in 2 significant figures. I have 3 there, so I'll just round this up to 1,400 grams of H2O liquid. Okay. So we did that with hydrogen. Let's do it with oxygen now. 1,500 grams of O2 gas now. Set up my fence post. And then so for every 32 grams, I think, of oxygen gas. 32 because oxygen is 16 and there's 2 of them. I get 1 mole of O2 gas. Right? And now I've got to do the molar ratio. This is a different molar ratio now. 1 oxygen mole, 1 mole of oxygen for every 2 moles of water. So for every 1 mole of O2 gas, I get 2 moles of H2O liquid. And then now the same thing as before, I got to convert those moles of water to grams of water, and so that's 18 grams of H2O liquid. Wow, that's really messy. I'm going to fix that. There we go. 18 grams of H2O liquid, and that's 1 mole of H2O liquid. Not H2O2, that's bad. It's not H2O2. Not hydrogen peroxide, that'd kill you. Don't drink that. Liquid, okay? So when you do that math, you end up with 1687.0. 2 sig figs, I'll just round it up to 1700 grams of H2O liquid. So notice, right, the one with the least amount is definitely the water, right? But I think the thing that is surprising is that there's such a big difference between 150. Whoops, sorry. There's such a big difference between 150 grams and 1500 grams, and you think that would be like the same would happen over in its products over here, but I mean that's a pretty close number comparatively, right? So you definitely have to go through and do these reactions, these reactants individually to figure out which one is going to be the limiting reagent. So you would say now, uh, the hydrogen gas, H2 gas, is the LR for short, limiting reagent for short, right? And that's how you answer that kind of question. All right, so there's this thing called theoretical yield, and that thing that's called theoretical yield is literally this right here. It's the amount of grams that you calculated stoichiometrically that you could make, right? And so that's called the theoretical yield. Like if you go through, if you have a number of grams of something, right, of a starting material, and you want to figure out what's the maximum possible you can make of that product using stoichiometric calculations like we just did right here, that's called the theoretical yield. And then we also have the actual yield, right? And this is the stuff after you do the reaction in the lab, right? You go weigh it out on a balance, and then you see what your yield is, and that's called your actual yield, right? And so if you take your actual yield, and you divide it by your theoretical yield and multiply that by 100, you get the percent yield. And so you're shooting here for getting as close to 100% as possible, and that means that you did a good job on your reaction, right? So let's just do a really quick example here. So with actual and theoretical yield, I would not use the rounded form of the product grams in there. I would actually use the unrounded, right, first, and then you can round later. And so I'm just going to use 1687 for this one. And so all I have to do here is percent yield equals, and then so for the theoretical, I calculated earlier, like in the previous slide, was 1687 grams, right? Times 100, and then let's say my actual yield was terrible, and I got only 168.7 gram. I do that math and I get 10%. That's terrible yield, right? You're shooting for something a lot closer to 100. But anyway, that's how you do a calculation for theoretical yield. I mean, sorry, for percent yield.